What's up, guys? Today we're doing Unit 1 in AP Chemistry, Atomic Structure and Properties, studying for that AP exam in May. So we're going to start off with the periodic table, which you should have a fairly general understanding of by the time you take the AP exam. And what you really need to know, you don't need to memorize all the elements, of course, that would be ridiculous, but what you really need to know is how to read the periodic table. So this number at the top here identifies the atomic number, or the amount of protons in that atom. It's also the amount of electrons when the atom is in its neutral state. You have the atomic mass, which is the number of protons plus the number of neutrons, and the mass of the electrons is not included because it's negligible. And it's the weighted average of the masses of different isotopes of the element found in nature. So in this instance, carbon-12 would denote that the most common type of carbon has 6 protons and 6 neutrons. And here you have a little bit of a more concise image of what the mass number identifies inside of the atom. Okay, so the periodic table can be identified into horizontal rows, which are called periods, and vertical columns, which are called groups. So you'll see the groups are split up into 1A, 2A, 3A, 4A, and they are also more commonly referred to by their names. So in yellow here you see alkaline metals, alkaline earth metals, halogen group, noble gases, nonmetals, and they all have very unique properties because they share valence electrons. Moving forward, also something you might want to know, when you move down periods, you're changing energy levels, so all the elements in the same period have their valence electrons on the same energy level. Moving on to moles. It's a very important concept you got to understand. It's going to come up in chemistry a lot. 1 mole is equal to 6.022 times 10 to the 23rd particles, or atoms. So this is called Avogadro's number, and it's a counting number that denotes the grams per the molar mass. So on a periodic table like this, you'll see the molar mass of the element listed in the top left corner. So basically 1 mole is equivalent to the grams of substance you have versus the molar mass on the periodic table. This is an important conversion unit that's going to come up a lot. You're going to have to solve a lot of problems with this. You'll memorize it over time. It's pretty easy to understand. Next up, you have molarity, and molarity is a way to define certain solutions. So the abbreviation is capital M for molarity, and it is equivalent to the moles of solute over liters of solution. So basically, you're asking, what is a solute, what is a solution? So a solute is the thing that is dissolved in a solution. So in the case that you're dissolving two of the same kind of substance, like liquid and liquid, it's the one that's in higher concentration. So moles of solute over liters of solution. For example, a 0.3 molar NaCl solution, aqueous NaCl solution, would have 0.3 moles of NaCl per 1 liter of solution. Moving on. Next up, we have percent composition, and this is basically just when you take a compound like CO2, and you take the mass of carbon, for example, which would be 12.01, and you divide it by the molar mass of CO2, which is 44.01, and then you do this calculation, And this is, and then you take this decimal number. Notice how these have four numbers, 4 significant figures. Notice how these have 4 significant figures, so the answer is going to also have 4 significant figures. Round this up. And then you multiply this figure by 100%. And you get 27.29%. So the compound is 27.29% carbon. And this is important for finding empirical molecular formulas. Empirical formula is basically the formula of the simplest ratio of the substance, and then the molecular formula is the actual amount of each atom that's in the substance. So electron configurations. When you do an electron configuration, it's pretty easy just to do it off of the periodic table. You start at the top. Every time you move down an energy level, that denotes a new energy level. These are the S group, the D block, the P group, and the F block. So when you're reading from left to right, if I want to denote the name for manganese, you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 1, 2, 3, 4, 5, 3d5. So when you go to the D block, you're going to go down an energy level, and when you go to the F block, you're going to go down 2 energy levels. Next up, we have Coulomb's law. Basically, all you got to understand is that Coulomb's law, the greater the charges, the stronger the attraction, and as you increase distance, the strength of attraction also falls off dramatically. Next up, we have the Bohr model. It's a simplified model of the atom that helps us understand energy transitions and how much energy is released or gained when an electron is excited. So if you have this electron jumping up to the 3rd energy level and then it falls back down to the ground state, this would be excited, this would be ground, this would be excited. When it falls back down, you get this wave coming out of energy. This would be some kind of electromagnetic energy. Let's just call it red light. So the Bohr model just helps us understand how electrons move around from energy level to energy level. Next up, we have photoelectron spectroscopy. Basically, it's when you shine some form of energy at some solid, and if the light energy is greater than the ionization energy, then it'll break the bonds holding the electron. It'll break the attraction holding the electron in place, and that will be converted into kinetic energy, and that electron will go flying. Then you have photoelectron spectra. And we can use photoelectron spectra to name the electron configuration of the atom. So over here, let's say we had so typically the origin will be on this side and it'll increase going this way. So it's all based on ionization energy. So the higher the binding energy, the closer to the nucleus the electron is. So in this instance, if this represents 2 and this represents 6, we could name this atom as 1s2, 2s2, 2p6. And that's clearly neon. Moving forward, we have some rules about electron configuration. So we have the Aufbau principle. Basically, electrons are placed in order of increasing energy. So the most interior electron is placed first, and then you go for outward. Pauli exclusion principle. If 2 electrons are in the same orbital, they have to have different spins. So when you have 2 electrons in the same orbital, one has to be spin up, one has to be spin down. Hund's rule. Hund's rule, basically, if you have, say this is the p orbital, 2p orbital, if you have 3 electrons if you have 4 electrons that have to go in, then each electron is going to take up 1 orbital first, and then you can go back and start doubling up on electrons. So, for example, what would the electron configuration be for the element sodium? Well, sodium has an atomic number of 11, so we know it has 11 electrons in its neutral state. So if we take sodium and we fill in its orbital diagram, we see that it looks something like this. And when you look at this, if you look at this and you try to predict what kind of ion it would become, well, we see that these electrons in here are actually really stable. And you have this unpaired electron right here that doesn't want that's not very tightly held. It's a valence electron, and the entirety of the 3 subshell is unfilled, so it's very loosely held to the nucleus. So if it's going to lose any electron, it's going to lose its outermost electron because it's most loosely held. So we see that Na turns into Na plus or 1 plus, but we usually drop off the 1 plus. Moving forward, periodic trends. So in terms of periodic trends, we have ionization energy, electron affinity, atomic radius. Atomic radius increases as you go down and across, because when you increase energy levels, electrons are farther out, and when you decrease electrons, there's less electron repulsion. Ionization energy increases across and up. Fewer energy levels, greater attraction to the electron. Fewer electrons, less electron repulsion, greater attraction. Electron affinity, as you decrease the amount of energy levels, it gets closer to the nucleus, which means a greater amount of energy is released when it falls down. When it comes into contact with the nucleus. Electronegativity increases and decreases the same way as ionization energy and electron affinity. So here's a more in-depth summary of the different periodic trends, and that's basically going to be it. If you enjoyed, please make sure to leave a like and subscribe. Thank you for listening, and I wish you luck on your AP exam.